Hello everyone and welcome back. Now, in the previous video, I showed you the method of integrating factors. Now, we saw that this method works for first order linear ordinary differential equations. Now, the real problem I have with that is the word linear. Remember, I told you 2 videos ago when we talked about classification and when we introduced linear versus nonlinear equations, the nonlinear equations are much more difficult to work with, right? They are just a huge headache. And in general, we cannot just solve nonlinear equations. If we could, I would be out of a job. But there are certain types of nonlinear equations that can be solved. And that's going to be the focus for today's lecture. So what we're going to focus on is first order differential equations. But in this case, they can be just any equation we want them to be. So here's how I'm going to write them. I'm going to say y prime is equal to f of x and y. Okay, so this is how I want to set things up. This is my differential equation that I'm interested in. Now, we've seen differential equations that already look like this. In particular, if this was just a linear function, then this would sort of fall into the category of the previous lecture. But what we're going to focus on is the nonlinear case, and in particular, we're going to look at separable equations. So we're going to say, if I could write my function f of x, y as a quotient, so m of x divided by n of y. So if I can write it like that, then the ODE is called, well, we call this thing separable. All right, so the title of the video, these are separable ordinary differential equations. What is separating here? Why do I call this thing separable? Well, it's separable because the x dependence and the y dependence completely separates out, right? I have an entire function of x and an entire function of y. They're not mixed together in some sense. And in this case, we have actually seen a separable equation already. Remember, in the previous video, we looked at integrating factors, and the general procedure at the end of that video was that I wanted you to solve this ordinary differential equation that looks just like that. Now, this may sort of hurt your brain for a second because I'm using different variables, right? Up here, I put things in terms of x and y. Down here, I put things in terms of t and mu. That's okay, right? If I just sort of relabel things, there's no issue. Y is my dependent variable, x is my independent variable, t is my independent variable, mu is my dependent variable. That means that I can write this thing like this. Right? So it's kind of a silly way to rewrite it. We don't like to write fractions over fractions, but the only reason I'm doing this is because this is sort of my m of t function, or m of x, and this is my n of mu function, or n of y, whatever you want to think of it. But what happened? I separated things out. And I am purposely using different variables here because I want you to get so good at differential equations. I don't want you to care if I start switching variables, right? I want you to be fluent in these things in such a way that you just have to say, okay, well, what's dependent, what's independent? Boom, I got this handled. So I want you to be fluent here, and I want you to recognize that we actually already encountered a separable equation in the last lecture. Also, we encountered how to solve them, right? We remember that we bring that mu over to the left-hand side. We put all of the mu's on one side, all of the t's on the other side, and that leaves us with something that we can just integrate up and away. Well, that's the general procedure. So let me illustrate this by example. So let's look at a different example. I'll go back to x's and y's to make everybody comfortable. Let's do y prime is equal to x squared over 1 minus y squared. Okay, now I went back to x's and y's. Hopefully you're happy. But this, now we can see that we've got m of x equal to x squared. And down here we've got n of y equal to 1 minus y squared. Good. That is a separable equation. We have separated out the x's and y's in this quotient. Well then, here's the general procedure. I'm going to follow in the same way that I found my integrating factor in the previous lecture. I'm going to multiply up the y's onto the left. And so I get this. And now I've got all y's on one side, all x's on the other side. Now I hit that thing with an integral. Now I'm going to do a little shortcut. Maybe you've seen this before because sometimes we're introduced to separable equations in a calculus class. But this is going to come from treating the Leibniz notation of the derivative, so dy by dx. Okay, that's called the Leibniz notation for a derivative. Differential of y with respect to the differential of x. I'm going to sort of cheat through this, okay? And this is sort of a mathematician's shortcut. So we always get to the same place in the end when we do this, but this just makes things a little easier. I'm going to keep the dy on the left, but I'm going to treat that thing like a fraction, and I'm going to take the dx to the other side. Okay, so maybe your calculus teacher is just screaming like, this is the worst thing you can do, right? We don't treat these things like fractions, and I agree with that. I would echo that same thing if I was teaching a calculus class. But I'm not, right? I'm interested in doing just a little shortcut, right? Because we know that if you follow the procedure, you know that at some point there's going to be a substitution. That's what we've had to do twice now, in the first video and in the previous one. And the result always comes up to be the same. So all I'm doing is, this is what happens when you do the substitution. So this would be 1 minus, say, s squared ds. Same thing, right? So just by treating that thing like a fraction, I saved a little bit of time, even though I spent a lot of time just explaining it there. But now I have some easy integrals, right? I can do this, even though, this isn't bad at all. So look at this. Y minus y cubed over 3 is equal to x cubed over 3 plus c. Don't forget about the plus c, right? We've seen it over and over and over again. This is a general solution to our ordinary differential equation. Now let's take some notes for a second, right? What's an issue with this thing? Well, it's an implicit equation. There is no general way for isolating for y, right? This is a cubic polynomial in y. Technically, there is a formula like the quadratic formula to find the roots of this thing, but it wouldn't even be worth it. It wouldn't tell us anything of value. So unfortunately, even though the method is easy, and even though it's easy to solve the differential equation, interpreting the answer can be a very, very difficult task. So here's what I want to do. I want to make my life a little easier. I'm going to multiply by 3 everything in this equation. So this is the same as saying, let's do 3y minus y cubed. Let's pull the x over to the other side. I want all of the x's and y's on the left. So minus x cubed is equal to c. And you're thinking to yourself, Jason, why didn't you write 3c? Again, this is another mathematician's shortcut. A constant is still a constant if you multiply it by 3. I don't know what that constant is. It doesn't matter what that constant is. So if I multiply it by all kinds of other constants, all that I need to know is that it is a number. This c is acting as a placeholder. It can help me to pin things down. If I had 3c there, then it would just add one more line of complication while I'm trying to solve this differential equation, right? I could have given you an initial condition here, and then you would have to solve for c, and eventually there would be a dividing by 3, and then multiplying it back in, and it would just be a whole production. So because this is just a constant, I don't care if I multiply it by other constants. I'm going to keep writing it as c. If it makes you feel better, you can call this thing d or C hat or C tilde, but it doesn't matter. It's a constant, whichever way you look at it. Okay, so what do we have? What are we actually saying? Well, what I've done by moving everything to the left-hand side here is I've said that we're actually looking for the level curves of a function. This function takes x's and y's, and what it returns to you is a single number, which is going to be 3 times your y value minus y cubed minus x cubed. So whatever that number is, that is what's going to be returned to you by this implicit function here. Okay, so how do we use this information to understand the solution to the differential equation? Well, what this is telling you is that solutions to the differential equation lie on the level sets. So we might have to remember some stuff from calculus here. They lie on the level sets of this function. Okay? So the question is, what are some of the level sets? Let's do a little sketching. Now, I'm going to emphasize the word sketching here. I am not a great drawer. But what you can do here is you can use all kinds of numerical software to print out some of these level sets. So something like a Wolfram alpha, if you put in specific values of c, it will tell you what the curve looks like. So for example, I went into Wolfram alpha before this. I put in my equation. I put c equal to 0. So I want to know the 0 level set of this function right here. Well, this is what Wolfram alpha gave me. Again, not the best drawer. So a nice sort of S-looking curve, okay? The important part is it goes through the origin, because if c is equal to 0, x and y equal to 0 is still going to solve that equation. Okay, so what can I do with this? Well, here's the thing. Imagine I gave you an initial condition. So I wanted to turn this thing into an initial value problem. How do I use that level curve in order to understand the solution to that initial value problem? Let's make it easy for ourselves. Let's say I wanted to give you y of 0 is equal to 0. Okay, so that's what this is right here. Y of 0 is equal to 0. Okay, so at x equal to 0, y goes through 0. That's what we know. Okay, then what does the solution of this differential equation look like? Is it just the whole big S curve? Can't be the whole big S curve. Why? 2 videos ago, I gave you the very final definition, and you might have laughed at it, but it was solution. And I said for something to be a solution, you have to be able to take derivatives. That's okay, right? Of course, this is a differential equation. I have to be able to take derivatives. Also, the solution has to be a function. Now, what do we know about functions? Functions have a property that they give you a single output for each single input. So for example, if I give you this value of x here, on this curve, I could return this value of y, I could return this value of y, or I could return this value of y. Now, if I return 2 or 3 of those values, I'm not a function anymore. I can only return 1. So the question is, what value will my solution with y of 0 equal to 0 return for me? Well, it's going to return the parts that are on this connected branch that it's close to. So what we can see here is that my solution, I'm going to draw it as little arrows. I like to think of x, so moving forward, I always think of my independent variable as being time. So my arrows are representing moving to the right. That's all that this is saying. But you can imagine a solution going through y of 0 equal to 0. And then as you increase the x, this is what the solution looks like, right? It's this little curve. Okay? But you can see some bad things happening, right? And especially, I can't go around the curve. Because if I go around that, then when I put in this value of x down here, I get this value of y, and I get this value of y. I can only go up to the turning point. Okay, now let's look at the differential equation. What does that turning point actually represent? Well, look at what the tangent line is doing. It becomes perfectly vertical at that point. It is an infinite slope. Well, good news for us, a differential equation is a slope equation, right? It's giving me the slope of that curve. So, where is that turning point? That turning point is when y is equal to plus or minus 1, right? Because that's when I try to divide by 0 and go to infinity. So here I turn around when y hits 1. Similarly, I could imagine going backwards in time, and I get something like this. So again, I'm using my arrows to denote flowing forward in x because I think of time sort of pushing us along. But that's just sort of to illustrate to you where the solution is. And of course, I can go backwards in this x until, again, I hit the singularity, and I've got an infinite slope of my tangent, and that's coming from when y hits minus 1. Okay, that's just one possible solution. I could have given you instead this value as an initial condition. So when x is equal to 0, I gave you, what is that going to be? The cubed root, or the square root of 3. Okay? So this could be y of 0 is equal to the minus square root of 3. Then we can ask ourselves, where does this solution exist? Well, we can sort of do the same thing. We can say, okay, well, I can clearly just kind of go as far to the right as I want. So this thing at least has a half open interval of existence. So what is that interval of existence? Go back to the definition of a solution. That's my alpha and beta that I gave you 2 videos ago. In this case, beta is positive infinity. I can go all the way this way that I care about. But if I try to go backwards, bad things happen to me, right? Eventually, my slope gets infinite, and I hit y is equal to minus 1. So that means that my alpha value is whatever this x is. I don't know it off the top of my head. It doesn't really matter. It's important to get the visual picture here above all else. Okay, I can do one more thing. I could give you an initial condition up here. So this is y of 0 is equal to the square root of 3. Well, what does the solution do here? Well, it can go forward in x until it sort of falls off this cliff, until I get to the turning point. But it can go backwards as much as it wants. So with 3 different initial conditions, I got 3 different intervals of existence for my differential equation. The first of which, y of 0 equal to 0, gave me finite alphas and betas on both sides. I can only go so far backwards in x. I can only go so far forwards in x. My second case, y of 0 equal to minus root 3. I can go all the way to the right in x that I care about. So beta is equal to infinity. But I can only go so far back in x until I eventually blow up in my differential equation. Same thing, if I have an initial condition y of 0 is equal to the square root of 3, well, I can only go forward to some finite value of x. That's my beta value. But I can go back as far as I want, and everything is okay then. And I want to remind you of something. This is just one level curve of the system. This is just the case where c is equal to 0. There are many, many, many other curves like this that do something similar for other initial conditions, right? All of the initial conditions I'm looking at are the ones that satisfy c equal to 0. But for example, you could have, just so I remember which way this goes, if c is equal to positive 1, you get a curve that kind of looks like it's tucked to the left here. So this is the c equal to 1 level curve. And you can do all of the same things, right? You see that the turning point here, again, is, well, this is supposed to be up a little bit further, but the turning point is when y is always equal to 1 or minus 1. That comes from the differential equation here. And then you could do the same thing for c equal to minus 1. And you can keep plotting these level curves. They all give you these beautiful little S shapes, and you don't even have to do any more math. Now you're just looking at pictures, and I could just pick a point randomly. I could say this point, that's going to be your initial condition for this thing. How far forward can you go? How far backward can you go? Well, if I'm right here, I can go backwards to right here, and I can go forwards to right here. I don't even have to do anything with math. Now I'm just using my intuition, and I'm sitting down and I'm looking at pictures, right? I let Wolfram Alpha do a little bit of the work for me, told me what these level curves look like, and then I took back over the captain's seat and I said, okay, thank you for providing me with the curves. Let me do the work from now on. Let me try and understand what this is telling me. Okay, so before we finish off, let's do one more example to really drive this home. So let's look at the following differential equation. dy by dx. So I'm going to write it in that Leibniz notation because we know that we're going to break it up with my little shortcut. And here, again, very clearly in the form of a separable equation. So this is my n of x term. This is my m of y term. Okay, so I've got all the components that I need here. I just need to follow the same procedure that I did in the last example. So I'm going to bring up this 4 plus y cubed. So I get 4 plus y cubed. I'm going to leave the dy. I'm going to bring the dx over here. Right? And we know we're going to slap some integrals around that thing, right? So when you write it on paper, or if you just turn on the video now, it looks like I just skipped a bunch of steps, right? Because a lot of the actual work is sort of happening while you're sort of putting things around this and putting the integrals on this. But that's sort of the advantage of using that dy by dx term and sort of treating it like a fraction. But now, again, I've got some nice polynomials, right? Nothing is going to be too challenging for me. So I get 4y plus y cubed over 4 is equal to 2x squared minus x to the 4 over 4. Don't forget plus c. Remember, we saw the real importance of plus c on the previous example, right? Because it helps us pin down level sets here. Okay, I'm going to do the same thing that I did in the previous example. I don't like these fractions. They make me uncomfortable. So let's multiply everything through. And, sorry, this should be a 4. And let's also put the y to the 4 on front because it is the highest exponent. So now I get y to the 4 plus 16y. That's coming from 4 times 4y. Pull all of the x's over here with us too, plus x to the 4. That's because I multiplied through by 4 as well, minus 8x squared. And this is equal to a constant c. So again, look at that. 1, 2, 3 lines of work. Hardest thing I had to do was integrate a polynomial here. All right, so maybe you might be forced to do some slightly more complicated integration, but nonetheless, this is a quick couple steps into the solution. That's not where the difficulty lies, though, right? We know that. The difficulty lies in trying to interpret this solution. So again, we're sort of faced with asking Wolfram Alpha or another one of these plotting software, something like Maple or MATLAB, to help us out. So I went ahead and did that for us. This is my xy plane. And what I'm going to do is I'm going to sketch a couple level curves for you. And I'm not going to label the values of c, right? So you can go through and just type c equal to 0. You can find what this thing looks like. C equal to 1, c equal to -1. You can try a bunch of different values of c. What I did is I put in a bunch of different values of c to try and get a characterization of what the solutions to this thing or what the level curves look like. Now, I want to dot out a very, very important value of y here. And this is the cubed root of 4. Okay, so while I'm drawing here, I want you, sorry, the minus cubed root of 4, I want you to try and figure out where that number came from and why it's going to be important. So this thing has a x to minus x symmetry. So we have this, and then we've got this, and then might have something like this, and maybe a smaller one inside here. Okay, while I was drawing that beautiful picture, did you figure out where the minus cubed root of 4 came from? Well, the way it's supposed to be drawn is it's supposed to be all of those turning points that we had from the previous example. How did I know that it was going to be at the minus cubed root of 4? Because that is the value of y that when y hits the minus cubed root of 4, bad things happen because my derivative becomes completely, I'm dividing by 0, and that means that I get a vertical tangent line. So how do we interpret this thing? Well, first of all, it might be worth trying to figure out what this function actually looks like. So if I put in, if I have a two-dimensional domain, x and y, I have this thing as a function from x and y into the real numbers, say z. And what it kind of looks like is two big mountains that look like this. So we have these two huge mountains, and then we have other level curves that are sort of looking like this. So these two huge mountains, that's these little circles right here. And then as you go down the mountain, your level curves sort of turn into these little almost sort of like figure 8 looking things. Okay, so that's just a sort of very, very inartistic rendering here. But how do we sort of use this information to understand what solutions to the differential equation are? Well, let me just start picking some points randomly, and let's try and figure some stuff out. What if I give you this point right here as my initial condition? I don't know what it is. I mean, we could figure it out, but it's better to do this pictorially. Okay, well, what is the region of existence for my solution? Well, it can go a little forward, but eventually some very bad things happen, and I don't exist anymore as a solution because I try to turn around on myself. Similarly, I can go a little bit backwards, but very, very bad things happen very quickly because my y value hits the minus cubed root of 4, and I try to turn back around on myself. Okay, then I could maybe ask myself, if I give myself this initial condition, what does my interval of existence look like now? Well, I can go for a long time forward in x, or what looks like a long time the way I drew this, but eventually bad things are going to happen. I'm going to blow up. Similarly, if I try and go backwards, well, I also will blow up. So, two initial conditions so far, both of them lead to blow up in forward and backward time, right? There is a finite alpha and a finite beta for both of these solutions. Okay, what if I give you this as my initial condition? Unfortunately, same problem. If I go backwards, well, eventually my y value is going to hit, and I get blow up going backwards in time. Similarly, going forward, well, it looks like you can ride the rails here for a really long time, but here now you can feel the roller coaster going off, and boom, we are out of room. Now, what I really want you to notice here is kind of how weird this is. The x and y values never blow up, right? I never have infinite x values or infinite y values, right? There's no asymptote on this graph. The asymptote is in the derivative of this thing. So this looks very, 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 very strange, right? What would a plot of the solution look like? Let's plot this little one down here because it's just way easier for me to draw. And let's put it right here, okay? So here, let's imagine this point right here is meant to represent that initial condition, okay? So what happens? Well, the value of y is increasing, right? I'm going up in values of y, and it's becoming steeper and steeper and steeper until the slope is infinite. So what's happening? Boom. And then I get my blow up. That x there is supposed to represent the blow up point. So that's when y is equal to -3/4, or the cubed root of 4. So this is my y, this is my x. Maybe I shouldn't use x here, but maybe an open circle or something like that. Same thing, going backwards gives me exactly the same thing. I'm increasing in y until I completely blow up. So it's really, really strange, right? It's like a big bang into existence out of nowhere. I go down and I exist for a little bit of time, and then I have like this big collapse and I just disappear. So if you're just like scanning across the values of x here, you go nothing, 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 big bang, oh look, there's something, big bang, gone, nothing. That's kind of what we're dealing with here, right? This is what I want you to get your head around, because this is the complexity of differential equations. So maybe 2 videos ago, I told you about the solution to a differential equation, and you scoffed. And you thought, whatever, Jason, it's not really that complicated, right? It's just a function, just some derivatives. I can do this. I took calculus. That's no issue. This is where we get to see the complexities. This is where the problems start coming up, right? It's when we have these blow-ups in derivative. Notice, again, there's no asymptotes here. Y never goes to plus or minus infinity. It always stays finite. The problem is its derivative blows up. And unfortunately, this is sometimes characteristic of very complex equations that people work on, that describe very physical problems. Things like potentially maybe the Navier-Stokes equation.